Good afternoon.
Hello, nice to see you.
Good afternoon.
Good afternoon, everyone.
Hello.
Hi, how are you doing, guys?
Fine, thank you. And you?
Doing fine too. Thank you.
Good afternoon.
Hi. So, short recall of our previous discussion. We main message to take home was to discuss the and find relationship between electric field and potential distribution. So we can initially we started to calculate electric potential difference between some points in space based on known information about electric field vector distribution in space. However, it's also possible to do it in the opposite direction when we take first derivative in respective direction and get out of it electric field. So that depends on conditions, could be beneficial to use either first or second approach. And let me maybe summarize this on our slides. Let me switch. So, where's my pen? So we have shown last time that if we have electric field as a function of coordinates x, y, and z, then electric field along each of these axes, x, y, and z, could be determined as follows. Ex will be negative first derivative. In this case, we can talk about first partial derivative because we take partial derivative of this function of x, y, z over x. Similar, we can write for electric field in the direction of y-axis. That will be minus dv over dy, and the same for direction z, will be minus dv over dz. If we are talking about vector form of this representation, because here we have just projections of electric field vector on different axes. So if we want to have it in a vector form, we need to use so-called gradient operator. So we have electric field vector is equal to negative. This is the sign for this gradient operator times v. And this gradient operator can be presented in a more clear form as follows. So here we have I unit vector, which defines direction along axis x, then d over dx plus j unit vector defines direction along axis y. Here d over dy and k unit vector d over dz. And here we have v, which is function of potential distribution in space. So electric field vector is actually negative gradient of electric field distribution. So we have electric field is a vector quantity. Potential is scalar quantity. However, we can define the direction of the fastest change of scalar quantity. In our case, it's potential. That direction is called the gradient of this scalar field of potential field distribution. And that is how we define the electric field vector. So in general case, when we have three-dimensional distribution of our potential. So that is summarizing our previous discussion. And now we would like to go one step further in terms of determining electric potential originated from continuum charges. So far, we were dealing with a point charge. So we have shown how we can calculate electric potential at some distance from point charge. Now we will use this approach in order to extrapolate it for a more general case when we have distributed electric charges in space. So let me go to another slide. And let us consider some arbitrary shaped body. And within volume of this body, there is distributed electric charge. And here is some point P, where we want to know the magnitude of electric potential. How do we approach this problem? Obviously, we need to divide this arbitrary shaped body in very small pieces, so small that with respect to this distance from this small volume of this body to the point where we want to determine electric potential, their size will be negligibly small, and we can consider these small volumes as point charges. So let us consider some small volumes in this body, and that will be, for instance, dq1, small charge, which is comprised inside this small volume. There are obviously many of such small volumes. For instance, we will have dq2. And there will be some distance from each of these small volume of this body to the point P. Here it will be R1. Here will be different, it will be R2. So we know how to calculate potential, electric potential created next to point charge. So since we deal with these small point charges dq1, dq2, we can in general write that small electric potential dV created by one of these small charges will be Ke, electric constant, dq in numerator, and distance r between the charge, like small charge dq, to the point where we want to determine this electric potential. Obviously, we remember about this superposition principle, and each of these small volumes, which carries small charge dq, will contribute to the total electrostatic potential. So we need to sum up electrostatic potentials created by each of these small volumes, small charges. So then the total electric potential V will be equal to Ke, which is a constant. So we take it out from integral, dq divided by r. So we need to integrate, like sum up contribution of each of these small charges originated in small volumes, which in total form the whole volume of this arbitrary shaped body. So in general, we need to consider two options based on this relationship between electric field and electric potential. So if electric charge distribution of this continuum charge possess some symmetry, then we should apply well-known Gauss law, which we discussed in details, determine electric field, and once we know electric field, we previously did this examples of how to calculate electric field of continuum charges next to continuum charges. Then we can determine the potential difference, for instance, between some 2 points in space, A and B, according to this equation, integral of scalar product, electric field vector, and displacement vector along the path between these points A and B. So that is first approach. If we have symmetry of electric charge, continuum electric charge, we determine electric field by applying Gauss law and then calculate potential difference between any points in space we are interested in. However, if there is no any symmetry in this continuum charge distribution, then we cannot apply Gauss law, and calculating electric field distribution next to this continuum charge will be an extremely challenging task. In order to make it easier, we first calculate electric potential distribution, because that's easier. We need just to deal with algebraic sum, not with vector sum. And once we have electric potential distribution, we can apply this transformation, like relationship between electric field and electric potential. So we have gradient operator of this electric potential distribution. So we can take partial derivatives of electric potential distribution along each of like directions of 3 axes, x, y, and z, and that will give us the resultant electric field vector in every point of our interest. So in both cases, we can get full information about electric field and electric potential next to such continuum electric charges. Let me now show you some example. I'm sure you remember we did something similar when we calculated electric field next to a charged disk. And we will do it in a different way. Now we will calculate electric potential next to this charged disk, and then take derivative, like first derivative, in order to determine electric field. And we will show that eventually we get the same equation for electric field as we did previously, doing a bit more complicated calculations when we directly try to calculate electric field without electric potential. So again, let us consider this system. We have two axes of coordinates here of our relevance. Then we have a disk. Which is charged with some surface density sigma. So we want to calculate electric potential caused by this charged disk at axis X in this point P. This is axis Y. So as we discussed previously, when we have a continuum distribution of electric charge, we need to deal with some small parts of this continuum. So we divide this surface of the disk in small surfaces. And the way how we do it, we can consider some radius r. Then we can move it by angle theta. So that will draw this side of a small element of this surface. And the other side will be just dr, change of this radius r. So as a result, we will have such small surface element and its area. So we can here put dr, like small change of this angle theta, d theta. So the area of this small element on the disk surface, dA, will be equal to r times d theta, that is this length of this part, and times dr, is kind of width and height of this surface element. So the total charge accumulated in this surface area will be dq equals to sigma times dA. And that will be sigma times r times d theta times dr. Okay, so we defined this, and now we want to know which potential, electric potential, this small charge dq will create at point P. So this small electric potential created by small charge dq will be Ke electric constant times the magnitude of electric charge dq divided by this distance. And this distance will be between this small element surface to point P will be r squared plus x squared, the coordinate of the point P where we want to calculate this potential. So this is coordinate x. Now let us substitute the expression for this magnitude of electric charge dq, which is here, into this equation. So that will be Ke times sigma times r times d theta times dr divided by square root r squared plus x squared, which is the distance between the surface element to the point P. So we have finished with the definition of small element, like small potential, which is created by a single small surface area. Now, in order to get the total electric potential at point P, we need to consider all contributions from every small element of this charged disk. So we need to integrate, as we mentioned on previous slide. So we need to integrate all over the surface of this disk. Let's assume that the surface of this disk is capital R. Now, in order to integrate all over the surface, we need to use like two integrals, one along R, because we have two variables here, like differentials, dr and d theta. It will look as follows. Total electric potential in point P will be Ke constant. Then also we have this sigma here, sigma, which is uniformly distributed electric charge density. So it doesn't change with coordinate, doesn't change from point to point on the surface of the disk. So we can also take it out from the integral. We have integral over this angle theta, then another integral over r, and here in the denominator will be r squared plus x squared. Any suggestions in which ranges we will integrate for theta and for
0 to pi and from 0 to r?
Yes, you are right. From 0 to 2 pi, so we go all around this circle, and from 0 to capital R means from the center of the disk to the to its edge. In that case, we will integrate all over the surface of the disk. So if we integrate first integral, it's quite simple. So we get 2 pi ke times sigma. And with the second integral, what we need to do, we need to have the same expressions behind differential as argument, like behind, like in this, under the square root in the denominator. So we have r in front of dr, so we can put it under differential, and that will be integral dr square plus x square, because x is a constant, so we can add anything we want in terms of constant, because differential of a constant will be 0. However, differential of r square will be r divided by 2. So here we need to, like 2 times r. Here we need 1/2 in order to compensate that, in order to stay in the same expression as was before. And then we divide it by square root r square plus x squared. So in this case, we can apply this tabulate, like table of integrals for integral x in the power of n dx. That should be equal to x n plus 1 in power n plus 1 divided by n plus 1. And in our case, this n is minus 1/2, because we have square root in the denominator. So let us write it here. It will be with 2 and 2 we can cancel out. So will be pi times ke times sigma. And our integral will be square root of r in second power plus x in second power divided by 1/2. And that will be from 0 to capital R. Okay, so if we now substitute, maybe let us write it on the next slide because we don't have space here. So let's rewrite this part. Ke times sigma pi, how it was in square root, square root r square plus x square divided by 1/2 from 0 to capital R. So that will be equal to 2 ke sigma pi. If we substitute r, capital R, it will be square root r square plus x square. If we substitute 0 instead of r, it will be just minus x. So that is the final equation which describes the potential distribution. Next to this disk, uniformly charged disk. And now our next step is to determine electric field. So electric field EX, because we remember, because of this symmetry of the disk and the fact that axis X is located, like going through the center of this disk, we get only Ex component of electric field. So Ex is equal to minus, like negative first derivative of potential over dx. Now let us take this derivative. So that will be minus 2ke sigma pi derivative of this first term in the parentheses will be 1/2 2x divided by square root of r squared plus x squared. So we take derivative of this square root first, and then we multiply by derivative of the argument under this square root. And that will be 2x because r is considered, capital R is a constant. So minus here derivative of the second term is simple, just unity. So now if we take into account this minus, we can rewrite this equation. It will be 2ke sigma pi times unity minus, here we can cancel out these guys, will be x divided by square root r squared plus x squared. So if you take a look on our previous discussion when we calculated electric field next to such charged disk, so these equations they coincide. So we have the same equation for electric field distribution, but in this case we approached it from the different way. We first calculated electric potential distribution next to this disk, and then took negative first derivative over the dx in order to derive this equation for electric field distribution. So now, before we finish the discussion of electric potential, we also need to come back a little bit and recall when we discussed electric conductors in electrostatic equilibrium. We mentioned that there is electric charge accumulated only on the surface of electric conductor. And now we want to provide more information how exactly it's distributed there, because there was one of these four statements which stated that the surface density depends on surface density of electric charge, depends on the curvature of the surface, and the smaller curvature, the higher electric density, means the higher electric field. So that is kind of dangerous moment if curvatures of electrically charged surfaces becomes very small. So we have like sharp areas, like some spikes on the surface that could cause to electric discharge and dangerous sparks or like analogs of lightnings between this sharpie area and surrounding. So that should be avoided. In order to understand this, we will have a discussion again about this conductor in external, a conductor in under electrostatic equilibrium. So if we have some arbitrary shaped body and there is some positive charge distributed all over this surface, then we know that at each point of this surface, electric field vector will be perpendicular to the surface. Means that if we consider some points A and B located on the surface of such conductor under electrostatic equilibrium, then if we go from one point to another along this surface, at each point on this path, there will be a condition that electric field vector times displacement vector will be equal to 0, because at each point, electric field vector will be perpendicular to the surface. Means that potential difference between points A and B, delta V, will be minus integral from A to B E vector times ds vector, dot product, that will be equal to 0. Means that the surface of electric conductor under electrostatic equilibrium is a equipotential surface, potential with the same surface with the same electric potential. There will be no potential difference between any points of this surface. What is also important to highlight that we know from previous discussions that electric field inside such conductor is absent. It's equal to 0. That means that the potential of any point inside this conductor will be also equal to the potential of the surface. So if we have, in order to make it more like visualized, if we consider some sphere which is positively charged, some charges on its surface. Here is the center, here is the radius. And if we show here the potential and electric field distribution, we will see the following. Here are some coordinate x. For potential, as we said, potential will be the same for any point inside this charged conductor under electrostatic equilibrium up to the surface, and then it will decrease. And that will follow this equation, which is Ke times Q, Q divided by R. This capital Q is total charge accumulated on the surface. When we deal with electric field, we know that inside the conductor, electric field is 0. Here is 0. Then at the surface, it reaches some maximum value and then also decreases. And that will be according to the following equation. Ke times Q total charge divided by R squared. So electric field will decrease faster than electric potential from the surface. Taking this all into account, let us consider two bodies, like two spheres, with different radius, which are connected with some metal wire, and they accumulate some charges, Q1 and Q2. There was initially some potential V1 and V2 of the surface of these bodies before they were connected with this wire. And since they were connected at this point, it becomes like one body, one conductor under equilibrium condition, means that their potentials become equal. V1 is equal to V2 and equal just to some potential V, which will be potential of the surface and volume of both of these bodies. So how can we calculate this potential V1 and V2? That is Ke times Q1, magnitude of electric charge accumulated at first bigger sphere, divided by R1. Let's say that is radius R1. This is radius R2. That should be equal to potential of the second sphere, and that is Ke Q2 divided by R2. Now, from here, we can find the relationship between the ratio of charges accumulated on these spheres and their radius. So we will have Q1 divided by Q2 equal to R1 divided by R2. Now let us consider electric field, which are created next to these spheres. So here we will have E2 and here will be E1. Electric field will be equal, like magnitude of electric field is equal to Ke times Q1 divided by R1 squared. Similar, we can write for the second sphere. Electric field next to the surface of the second sphere will be E2 equal to Ke Q2 divided by R2 squared. So now let us take a ratio between E1 and E2. So E1 to E2, that will be Q1 divided by Q2, and here will be R2 squared divided by R1 squared. Okay, up to this point is clear. So now we actually know what this term will be equal to. We have shown previously that Q1 divided by Q2 is equal to R1 divided by R2. Let's substitute it here. We get R1 divided by R2 times R2 squared divided by R1 squared. We can cancel this square and these guys, and eventually we get R2 divided by R1. So the ratio E1 to E2, the ratio of the magnitude of electric fields next to the surface of first and second spheres will be equal to the ratio of the second and first sphere radius. So now, if we look at this, let's write it here. E1 divided by E2 equals to R2 divided by R1. If, for instance, we have small sphere radius R2 approaches to 0, so it becomes very small and like kind of Sharpie edge of this system. Then E2 approaches to infinity, because if this approaches, this ratio approaches to 0, then this ratio should also approach to 0. That will happen only when denominator approaches to infinity, because numerator is not equal to 0. So we will have electric field because there is some charge on the surface of the sphere. So we see a clear dependence on the strength of electric field with the radius of the like curvature of the surface. And we have shown before that there is a direct relationship between electric field and sigma surface density of electric charge. And that is important to highlight. If we reduce the radius of the curvature of the system, we increase the electric field strength, and that is happening in parallel with the increase of surface density of electric charge residing on this area. So why it's important? Because actually could be quite a dangerous situation when we deal with high potential equipment. These effects can cause glowing of like ionization of like very strong electric field, can cause ionization of air molecules. They start to emit some light. That already losses of electric energy, specifically kind of a problematic issue for these power lines which transmit electricity at very high potential difference. And also can happen some literally electric discharge, which will short different parts of equipment and cause short circuit, which will switch off the electrical equipment. So that's why it is necessary to pay attention also on the design of these surfaces, which can be of conductors which are under operation, staying in this condition of electrostatic equilibrium. So there is this breakdown electric field for air is 3×10⁶, like 3 million volts per meter. So under normal conditions, air, this medium, is an insulator. So if we detach wires, like cut wires, the electric current stops flowing through the circuit because air does not conduct electricity. But if the potential difference is very high, so it creates a strong enough electric field between these two separated by air conductors, that will cause ionization of air and eventually will create a short circuit, which should be definitely prevented. Okay, guys, then thank you for your attention. That's everything what I wanted to tell you about potential. Have questions, you're welcome. we will continue our discussion on Monday, and that will be a new topic focused on capacitance. So we will introduce the concept of electrical capacitance and also of obviously of electrical capacitors, some systems of two conductors which are designed to accumulate electric charges. So we will learn their basic characteristics and also how total capacitance of a battery connected in series or in parallel of different capacitors will be calculated. But that will be already our next topic for discussion. Okay, then thank you very much for attention. Have a good weekend. Take care and see you on Monday.
Thank you. Goodbye.
Thank you. Goodbye.
Bye-bye.